What if I told you that a single line of text typed into a search box could make a website behave in ways the developer never intended to do it? So that's basically cross-site scripting, or more commonly known as XSS attack. And today we'll understand three major types of XSS attacks, why they happen, what problem each one is trying to solve, and we'll check it out inside CyberGYM. So let's dive into it. At its core, XSS happens when a website mistake user input as trusted code. So instead of displaying your input as just plain text, uh, the app should have actually sanitized whatever your input text is. The browser ends up executing whatever text you have given as code. There are three types of XSS attack, and the only real difference is where the malicious input actually resides. Sometimes it exists inside the browser itself. Sometimes it's reflected back by the server, like reflected XSS type, and sometimes it ends up being permanently stored inside the database so that whenever everyone visits your web page, they get served malicious content. So let's get started with DOM XSS. In this case, the server isn't actually the problem. The vulnerability actually exists entirely inside the browser. So why it happens is modern web applications constantly read values from the URL, like search boxes or page elements, to update what you actually see. If the page blindly trusts the data, and if it ends up inserting it into the page without it treating it as just plain text, what the browser actually does it ends up interpreting whatever the input is as code instead, and then it would execute and it would end up showing you malicious content. The challenge here is recognizing when the front end is handling your input in an unsafe way. Reflected XSS works slightly different. So what happens here is your input travels all the way back to the server, and the server immediately sends it back as part of the response. So if that response is not properly encoded, the browser again might execute it instead of displaying it safely. So the important thing to understand is that the payload isn't actually stored anywhere here as well. It only exists as part of your single request that is sent to the server. So that's why it's called as reflected XSS, which is commonly associated with malicious link being shared through emails or messages. So this is where phishing actually happens. Phishing generally happens through reflected XSS attack. Now, stored XSS, this is usually considered one of the most serious type. So here what actually happens is instead of disappearing just after one request like reflected XSS, the malicious input actually gets saved by the application itself. It gets into the database. So typically your input gets saved by the application inside the database, and every time someone loads the affected page, that stored content is delivered back to their browser. So the real problem isn't just accepting bad input at this point. It's serving the same input to every future visitor as though it was just trusted content. So that's very, very scary. Even though these three attacks work differently, they all exploit the same underlying concept or mistake: trusting user-controlled data without actually handling it safely. That's why secure application focuses on treating all user input as untrusted. So that way nothing escapes. So by validating it on the server end and enforcing browser protection like CSP or content security policy, you fix the problem by eliminating the root cause behind all these three, and then you gain the trust. Now that you have understood the difference between DOM, reflected, and stored XSS and why it actually happens, you are ready to understand what the challenge is with the right mindset. Remember, you should always practice these types of CTFs in a safe environment or in environment that you own and you have permission to test. Or you can use training platforms like CyberGYM. So let's get into these vulnerabilities in action. First, I'll solve it manually, and then let's compare it with HackerGPT, and then we'll figure out which is the best possible way to go ahead. So out of the three XSS attack, let's start off with DOM XSS attack. As you can see, I'm at CyberGYM, which is our test target, vulnerable web application by HackerGPT. Let me head over to the side navbar, scoreboard. Here is where you will see various challenges. I just filtered out difficulty level 1, XSS, DOM XSS. Okay, perfect. Perform a DOM XSS attack with an iframe. Source equals JavaScript message, right? Okay, what's the JavaScript message? JavaScript message is XSS. Okay, perfect. Let me check out the hint as well. Yeah, look for an input field where the content appears in the HTML when the form is submitted. Click to unlock another hint. Let me just click. Okay, the challenge is almost indistinguishable from perform a reflected XSS attack if you do not look under the hood to find out what the application actually does with the user input. Okay, great. So before I even think about testing for XSS attack, I always ask myself one simple question: where does the input that was mentioned here actually come from? So one of the first thing I noticed over here in CyberGYM is that whenever you filter out something, you can check out in the URL as well, which shows that cybergym.hackergpt scores difficulty equals 1 and categories equals XSS, right? So whenever I type something into the search bar, or if I just filter out, it appears in the URL. So this is an interesting clue. But now, does that mean that the changing URL actually means that there's a DOM XSS vulnerability? Certainly not at all. So thousands of websites update the URL when you actually search for something. But as a security tester, our intuition should be that we should consider that as a hint that my input is being stored in the URL. And therefore, there's a good chance the page JavaScript is reading that value to update whatever I see. So in the hint, you can see that there's a message saying input. So now that's a good hint. So what are all the various input fields that are there in this particular page? Let me check it out. Let me read the hint once again. Okay, understood. So there's one input field in the search bar right next to the account, and there's another input field, right, to filter out various challenges that's available in the scoreboard. Let me see the site now also once. Yeah, are there any input fields over here? No. Okay, let me go back and copy the iframe that was intended. Let me copy and let me paste it over here and see. Okay, no challenges found. And there you go. In the URL, search query equals iframe. Okay, so there was there you go. The iframe was put into the search query as well in the URL. So thousands of websites actually update the URL when you search, right? So, but as a security tester, it's you should always consider that as a hint, and the hint is it's being stored in the URL, and there's a good chance the page JavaScript is reading the value to update what I see. So, what is my thought process? My input is in the URL. The browser is probably reading it, and let's see how it actually handles it. So that's exactly why I started with the search box. Search box functionality almost always reflects your input somewhere, whether it's a result, whatever you are looking for, the specific card with that specific challenge, or it's a uh, search title, or the part, it could be a part of the page itself, like in the search bar you type something and then it redirects you to a particular page. It makes the search bar one of the most highest value places to begin looking for a DOM XSS. So that's the intuition. Now let's test it in theory. So we already pasted in the search bar for filtering out the categories of CTF challenges, right? Let's try to paste it next to the account. There you go. CyberGYM.hackerGPT says XSS attack. Notice what happened. I didn't upload any file. I didn't send a special request to the server. The browser itself processed my input and it rendered it as part of the page. That's why this is called DOM based cross-site scripting. The important thing here is to understand is that the search bar isn't actually the vulnerability. It simply is where I just entered my data. I could just enter a plain text, or I could enter a code. The real issue is what happened afterwards. The application JavaScript took that data from the URL and it ended up inserting it into the page itself in a very unsafe manner. Instead of treating it as a plain text, the browser ended up interpreting it as an HTML. And that's the key intuition behind the DOM XSS. You're not randomly trying out various payload in every input field you're looking. You're just looking for those specific places where your input is likely to flow through the browser and be rendered back to you into the page. So, what's the intuition like? Search boxes, URL parameters, or filters, and anything that basically updates the page dynamically are generally a great starting points, because that's exactly where front-end JavaScript is most active, right? So remember, the changing URL wasn't just a proof of a vulnerability, it was a evidential clue, I would say, that led us to investigate this vulnerability. So the vulnerability was in the browser and how it handled data after reading it. That's why sanitizing user input is very, very important. And there you go. Whatever the search product was there, it didn't find. And that's how we completed DOM XSS. Now let's check out Reflected XSS. Perform Reflected XSS attack with iframe source equals javascript.alert XSS. That's why the hint had already told us that DOM XSS and Reflected XSS is very similar, unless and until you look under the hood. And as I had mentioned earlier also, Reflected XSS sends a message to the browser and in a single response, and the server responds back, and the browser shows us malicious content. So let's try to see how that works. Okay, now I'm going to show you how HackerGPT solves the DOM cross-site scripting challenge inside the CyberGYM. So let's go ahead. In the scoreboard, I'm going to copy the DOM XSS challenge, which is perform an XSS attack with the following iframe. I'm just going to copy this And in the CTF mode of HackerGPT, saw the following challenge. For the following target, we need to give our test target also, right? So let's see how HackerGPT solves it, and here are the hints of it. Okay. Very similar to the Reflected XSS, right? So this is the Reflected XSS. Okay, I'm just going to do inspect element. Let me check location. Where is this? Okay, these are all the places where location is there. Let's see what HackerGPT is doing. Okay, inner HTML. Yeah, inner HTML. Okay, just like that, HackerGPT did end up solving our DOM XSS challenge. Great. With the following iframe XSS. Okay. Perfect. Yeah, that was fairly simple. So yeah, HackerGPT analyzed the page. It did end up identifying the search functionality inside user input directly into the DOM using inner HTML. That's why I was using inspect element to find out inner HTML and figuring out the corresponding place where we could put the iframe. So HackerGPT immediately told us that the vulnerability is DOM XSS. Let's read it out. Okay, so the challenge is solved. How it started. Okay, how it worked. Search functionality that renders user input. Okay, the payload was the iframe, and the application verified the successful XSS creation via frontend. Okay, if I paste it in the search bar, it doesn't, but if I paste it in the search bar next to the account, it does happens. Perfect. XSS equal to manual. Yeah, whatever alert message we end up giving, it solves. Let's try to solve the bonus payload question also, which remains unsolved, right? We didn't do this manually. Okay. Yep. So the bonus.
When you wanna shop online, then you had better be sure the experience is safe to a joyous song and say, Choose shop, choose shop. You can order tasty beverages in any quantity. Choose shop, a hit up. It has got more holes than a warehouse. So in conclusion, I would like to say a final thing or two. I won't be shopping at the Chew Shop with my coupon code for June.
So that was the bonus payload. Okay, let's actually copy this and give HackerGPT as well to see if it can also solve it. And let's go to the memory tab to see the exploitation progress. Okay. Yeah, HackerGPT is solving. That's great. So what actually happened? So what it did was it injected the required payload into the vulnerable search field, just like we did. And when the page updated, that is, when you refresh the page, the browser renders the injected iframe. And that iframe executes the JavaScript, triggering the alert required by the challenge. But the interesting part is HackerGPT didn't just stop right after that, right? Yep, DOM XSS challenge. Okay, let's check it out. Bonus payload. Did it solve the bonus payload?
You had better be sure this is safe and also secure. Don't wanna let no SQL or cross.
So let's see how HackerGPT did it. The SoundCloud iframe was injected into the search field, rendered into the DOM via inner HTML, and the application's verify local XSS challenge event. Okay, this is important. Confirm the successful DOM XSS. Okay. As a bonus, the SoundCloud widget actually loaded and played on the CyberGYM page, a much more stylish XSS than a simple alert. Okay, yes, makes sense. So, yeah, what actually it did was it verified that the challenge was completed. Like CyberGYM internally emits a socket.io event called verify local XSS challenge, and HackerGPT ended up detecting that as a verification event, and it confirmed that the exploit worked successfully. So instead of simply using that, hey, here's a payload, it explained where the vulnerability existed, why the payload executed, and how the application actually confirmed the success, which is much closer to how we would also do. But we got the visual cues, right, of the challenge being completed. Now I want to push, and I did push it further. So instead of just the JavaScript with the message XSS, I also gave it the SoundCloud embedded challenge, and instead of executing just the alert box, it also figured out how to inject the payload with the actual SoundCloud player inside the vulnerable page. And why did it work? Actually, that's a good question again, because again, the application isn't just allowing JavaScript, it's allowing arbitrary HTML also to be inserted directly into the DOM. Earlier, in the XSS being the message, it was just sending JavaScript, but now we figured out that it's not just allowing JavaScript, it ended up allowing any arbitrary HTML. So you can end up giving any embedded HTML code, not just the SoundCloud. So the browser simply treated the iframe as legitimate page content, and the result is basically that the vulnerable application now suddenly just showed us that the embedded music player actually works. And because it reminds us that cross-site script is not just alerting pop-ups, and if an attacker want to inject any arbitrary harmful HTML, they can actually modify the page and display fake login forms, and that's generally how phishing activities work. They end up embedding external websites or completely change what the users see altogether. So the alert box is, for us, is just only a proof of execution, whereas the real attackers usually use very creative ways to trick people. So why this matters? One thing is what I really liked about HackerGPT solving is it gave us a good reasoning explanation. It did end up identifying the vulnerability the same way we did. It recognized the unsafe DOM operation. It chose the appropriate payload, and it also verified the successful execution, which I didn't know that there was a verify local XSS challenge event that was there. And again, with respect to phishing, why it is a bit scary is the URL of the page would pretty much look the same, right? They wouldn't have changed it via tiny URL or anything. Let's check out the payload once. Okay, that's the post. Yeah, that's the post request with the socket.io. That's the verify local XSS change event, I guess. Right? Okay. I'm just going to save that payload also. Let us check out our payloads. Yep, DOM XSS solved successfully. In the memory tab, you can see the entire workflow of what happened and how we did it. Okay, that's the iframe. Payload exploitation progress. DOM XSS challenge solved via successful functionality. The application uses verify local XSS socket IO event to verify the XSS payload, which was successfully injected into the DOM. The successful. Okay, that's our target scope and the flags, both the flags. Now I'm going to show you how HackerGPT solves a reflected cross-site scripting, or generally known as Reflected XSS challenge inside the CyberGYM. Now let's see how HackerGPT does it. So this is the result. Let me go back to the scoreboard, copy Reflected XSS, all the following CTF challenge, all the following test target. Let me copy the test target, CyberGYM URL, and let's see. Browser inspection, fetching, and yeah, just like that, it did solve it. Let's see what it says. Right, it says vulnerabilities reflected cross-site scripting, search query parameter queue. Okay, and payload is the same iframe that we saw, and exploit exploit is there in the URL. So search q equals, and then we see our payload. And okay, let's check out the message. Okay, this is our payload. Okay, memory. Okay, perfect. Let's check out the exploit URL once, right? Yeah, let's check out the exploit URL. We got the alert saying CyberGYM.h HackerGPT says XSS. Yeah, so HackerGPT began analyzing the application, and instead of looking for stored input, what it did was it found out the vulnerable DOM manipulation. It examined the application's URL patterns very quickly, and it identified the vulnerable parameter called the queue parameter. Okay, which is the search query parameter. So it found out the queue parameter, which is called as the search query parameter. It notices whether the value is placed inside the queue. And here, as you can observe in the URL, it says queue equals iframe and something, right? So what happens is, whatever the value that's placed inside the queue, it gets reflected back into the web page without proper output encoding. That immediately told HackerGPT that this is reflected XSS vulnerability. So instead of typing into a search box, it built it specifically crafted for this URL. So the queue parameter, which contained the iframe, when the victim, or in this case our browser, opened that URL, we got the alert message of CyberGYM.HackerGPT saying XSS, because it rendered this specific iframe and it executed the underlying JavaScript message. The familiar alert box came, like how we did it for the DOM XSS attack, right? So it just didn't assume that this was successful. Again, as I had showed earlier in the payload, it checked that the application emitted the socket IO event, and it found out that the verify local XSS challenge was there. And HackerGPT reobserved this specific event, and it confirmed that the challenge was officially completed. So that kind of explanation is very important. So now you might be thinking, why reflected XSS matters, right? So why is this even considered dangerous? If the payload isn't permanently closed, the answer is because the user can be tricked into visiting any malicious link. Like imagine you're actually receiving an email that appears to come from your bank. And inside this legitimate looking email with the legitimate domain address, inside the hidden inside the URL, there's this hidden iframe, right? So this is a reflected XSS payload. If the website is actually vulnerable, the attacker can execute immediately after the page loads once you click on it. So depending upon the application, that could be used to steal session tokens. It could be used for modifying your page content. It could even capture your sensitive information or impersonate legitimate functionality. Like the alert box which you saw in this CTF challenge is simply just proof that the JavaScript execution is actually possible. But in real scenarios, real attackers usually, as I had mentioned earlier, replace these alerts with something much more dangerous. Now, finally, let's get to the final challenge, which is Stored XSS. In this challenge, the objective is a little different from the previous XSS lab. We are asked to perform a persisted or stored cross-site scripting attack. So let's head over, let's enable CTF mode, head over to scoreboard, API only XSS, perform a persisted XSS attack with the iframe. Again, it has JavaScript alert message of XSS without using form. Okay. So we are basically not allowed to use front-end application at all. So everything must be performed directly against the application's REST API. That means no browser interaction, no forms, and no manually entering the payload into the website. Right. So instead, we need to identify an API endpoint which stores controlled data without properly sanitizing it, because that's the main way how we can execute a cross-site scripting attack. Because the vulnerability exists where user input is not being sanitized properly. So let me ask HackerGPT. Let me copy it. Copy, paste. Test target. Copy the following CTF challenge. Perfect. Okay, it login, feedback, contact, captcha, feedback once again, products, X 11. Products. So you might be wondering, the first thing what HackerGPT did was it authenticated with the application by logging in. Since API request requires authorization, it logs in by sending a post request to the user login endpoint. Once authentication actually succeeded, the application returns a JWT token, which basically means it provides a stateless authentication, which is self-contained data and is important for secure scalability of modern web applications and API. So what HackerGPT did was it automatically stored this token and it will use it for subsequent API requests. At this point, HackerGPT is already authenticated and it is ready to interact with the backend entirely through REST calls. Right now, because it has the JWT token bearer. And what's the next step HackerGPT did was it started checking out where the vulnerable endpoint is. Now comes the interesting part, because instead of immediately trying to inject payload anywhere, you can see HackerGPT is figuring out all the endpoints which probably does not sanitize, right? So it tested for a different location where user control data can be stored. Like one obvious candidate was it already showed was feedback API, since users can submit comments. However, HackerGPT quickly discovered that this endpoint actually sanitizes HTML before storing it, so it's no point going down this rabbit hole. So when the XSS payload is actually submitted here, the HTML is actually stripped out, preventing any script execution, which is actually ideal. But in our case, we are trying to exploit it. So rather than forcing attack in this point, HackerGPT moves and continues, and it starts looking for another endpoint. This is an important step because real penetration testing often involves identifying which inputs are properly protected and which is not. Next, HackerGPT found out the products API. Specifically, it looked into the product description field. Okay, we got the result. So unlike the feedback endpoint, this field does not sanitize as HTML. That immediately makes it a strong candidate for stored XSS vulnerability. So based on this intuition, HackerGPT sent post request to create a brand new product inside the product description. It inserted the required iframe payload inside the request, and it sent it directly to the REST API without opening the front-end application at all. So what happened is the server accepted this request, it created the new product, and it returned the response. And most importantly, the response shows that the iframe payload has successfully been submitted. So at this point, nothing had escaped, nothing was removed, and the malicious HTML is theoretically permanently stored inside the application's database. So now let's just check out what HackerGPT's response is. Key insight: the feedback API sanitizes users' input, as I had mentioned. Comment field is stripped. The product API does not sanitize the description field, assuming it the correct attack vector for API only persisted attack. The entire attack was performed without touching front-end application, purely through REST API calls. Authentication via API. HackerGPT, as I had mentioned earlier, logged in as admin using post rest/user/login with the credentials. It also found out admin credentials. It discovered the vulnerable endpoint, which it discovered various endpoints, right? API feedback endpoint, which actually sanitizes. So this is not the right part. And API/products endpoint does not sanitizes the description field. Exploited the vulnerability. It created the new product via post API products with the XSS payload. Okay, let us quickly check out what the payload is. Okay, this is the payload name XSS test the product name itself is XSS test product. The description is where our iframe resides. Okay, it gave 1.99 as price. Okay, so the product was crafted with XSS payload persisted in the database. The response confirmed that the response meaning that it used the socket.io. Let us check in the categories. Let me search for XSS. Yes, and we got the alert message also. And when I click on the particular product of XSS test product, our alert message also came. Right, so HackerGPT did end up creating the product. Again, whenever I click on it, we get the alert pop-up. Let me check network payload. Let me save this payload so that I can use this payload when testing it manually. Save as payload. Let me check in saved. Okay, memory target is this application. CyberGYM, it performed recon initially and it found out the endpoints, which is API products. It found API feedbacks. It also found out login, and it found out the captcha endpoint. Credentials, it found out credentials also, and JWT token. Okay. Attached. Okay. And vulnerabilities, API only XSS. The API products post endpoint does not sanitize the description field, allowing persisted XSS via product creation through the API without using this front end. Okay, exploitation progress. Logged in via post. Created XSS. No, let's try it manually now. So now I'll demonstrate stored XSS or API only XSS manually. To demonstrate this, I'll be using Burp Suite together with the payload that HackerGPT previously had identified, right? So let me launch the browser and let me type CyberGYM gpt.app. Okay, this is the categories. Let me go to the scoreboard. Okay, we're in the scoreboard. API only. Perform a persisted XSS attack with the following iframe. So in Burp Suite, I launched the Chromium browser using the HTTP browser feature. In the latest Burp Suite, it is available. I am not sure if it's available in the previous versions. I think in the previous versions you have Firefox. So the browser is already configured to send all traffic through the Burp's proxy, allowing me to inspect every HTTP request the application makes. Okay, that's the second hint. Okay, and that's the third hint. Okay, now let me head over to the HTTP proxy. It has intercepted all the requests. Let me put in filter it for search. These are all the requests with the term search. So once I switched over to HTTP history tab inside the Burp Suite, here as you saw, every request between the browser and the server is available. And instead of generally scrolling through all of it, filtering is the best way to narrow down the result, right? So we were quickly able to find the request to the application's product search endpoint. API issue. Okay. REST products search queue. Yes, this is what we would need. Let me send this to the repeater, and it's available in the repeater. Let me check out the headers. It's a GET request. I'm changing it to the POST request. Apply changes. What's the path? Let me remove the search from here. REST to API products. Okay, let me go back. Value is queue. Let me delete that. Okay. This is my token. JWT token bearer. Okay. Host is CyberGYM. Cookies. Okay. This is one of Burp Suite's most powerful features, I would say, because I can experiment with the request without repeatedly using the browser. So inside repeater, you can modify the request. Like the original GET request is now modified to POST for this attack. I can also update the request body with the JSON payload that HackerGPT had previously generated, which creates a new product. Let me paste that. Okay, perfect. Since HackerGPT had already identified the endpoint as failing to sanitize HTML, I just quickly moved into this particular endpoint. I have XSS features, name is XSS features. Okay, yeah. Okay, now everything looks correct. I am just going to change. Okay, best. Based on the categories and success. Yep. Let me send it once again. Yep. Okay, it's successful. So it has successfully created a new product with the image of the best CyberGYM artwork thing. Let me check in the GET request where all the products are there. And there you go. Let me retry this. Let me just send it once again and success. And just like that, we were able to do it manually. API only access is completed. So what actually happened? The server processed the request and it immediately sent the successful response, right? So the response confirmed that the new product has been created. The product description still contained the iframe as it was submitted. Nothing has changed or nothing was removed. The payload was successfully stored inside the application's database. Again, I didn't even check in the front end. I checked in the GET request where all the products was there, and our newly created product with the payload was also mentioned. So the description, it still contains the iframe, and seeing the payload returned directly from the API, it confirmed that the malicious HTML has been permanently stored.